In a bombed-out field in occupied France, 1941, a team of German engineers approached the wreckage scattered across the muddy terrain. What they found wasn't just another downed Allied fighter.
I've never seen anything like this.
It was a puzzle that would haunt them for months.
How could it have happened?
A technical mystery that would challenge everything they thought they knew about aircraft design. The mangled fuselage of a Spitfire lay there, half buried in the damp French soil. And in that moment, the eyes of those men locked onto something that would shake them to their core. Why that Spitfire demanded such intense study was brutally simple. Throughout the Battle of Britain and beyond, the British fighter had owned the skies with a dominance that confounded even Germany's elite pilots.
This design,
the Bf-109, the Messerschmitt, was a formidable machine, fast, powerful, deadly in a vertical climb. But the Spitfire had something the 109 didn't, almost impossible agility. It could turn in tighter circles. It could climb, roll, dive, and vanish into the clouds like a phantom. German pilots reported with mounting frustration that once a Spitfire committed to a tight turn, you couldn't beat it without a height or speed advantage. And that was what was killing them. By 1941, this was more than just a technical problem, it was a survival issue.
The turning radius of the Spitfire
Hundreds of German pilots had learned the hard way that turning to fight a Spitfire was a death sentence. The Bf-109 had been designed with a crystal-clear philosophy. Build the fastest, most powerful fighter capable of penetrating enemy formations. The Spitfire, though, operated by different rules. Something in the structure of those British wings let it do what no other fighter could: sustain incredibly tight maneuvers without losing lift. The German engineers knew the answer lay in the wing design itself.
We're looking at the curvature here.
Why? And now that wing was there, damaged but intact enough to be studied. The engineers began dissecting the wreckage with surgical precision. The wing's curve, the weight distribution, every internal rib, everything was measured, documented, analyzed. The Bf-109's wings were angular, straight, efficient, pure logic. A designer's pragmatic choice when speed and manufacturing simplicity mattered most. That Spitfire wing was something else entirely. There was an elegance to it, a smooth curve that rippled along the entire length as if frozen in metal and fabric. The architect behind this was R.J. Mitchell, a British engineer whose vision rejected everything conventional wisdom said worked. While German designers pursued raw power, Mitchell pursued aerodynamic perfection. Years working on racing seaplanes had taught him something fundamental. Raw size and power mattered less than how air moved around a wing. And this philosophy was written into every line of the Spitfire, evident in its performance, in every outturned dogfight that left German fighters behind. The German engineers didn't know Mitchell's name or his design philosophy.
It changes everything.
But as they tore apart that destroyed Spitfire piece by piece, the truth became undeniable. This wasn't just a better aircraft. It was a fundamental repudiation of everything they'd built their entire fighter fleet around. They worked methodically, drawing, measuring, documenting every curve and dimension. Berlin wanted answers. They wanted to know how the British had cracked this. Rumors circulated about plans to copy the design or at least steal its secrets for future fighters. But something darker was becoming clear in that ruined French field. What they were looking at couldn't simply be copied. The design philosophy was woven into every aspect, from the tip of the wing to its root. You couldn't just replicate the shape. You'd have to rebuild your entire approach from the ground up. As they measured the wing's curves in detail, the scope of the problem crystallized. The Spitfire's wing wasn't built like conventional aircraft. It was a masterpiece of proportion, a sequence of curves creating what aerodynamicists call laminar flow profile. This shape allowed air to slide over the wing with an efficiency and smoothness that the 109's angular design could never achieve. The calculations they recorded violated everything they thought they knew about aerodynamics. Those curves should have made the wing heavy, dragging the whole aircraft down. But the data told a different story. Strong, light, and apparently impossible. The more time those engineers spent analyzing that captured Spitfire, the deeper the problem ran. Those wings weren't just letting the Spitfire turn better. They seemed to be rewriting the rules of flight itself. As data accumulated, a grim truth crystallized. To match the Spitfire's capabilities, Germany would need to overhaul its entire fighter philosophy. Above them, the Battle of Britain raged on. Pilots died. The war went on. But in that field in 1941, while those engineers mapped and measured that captured fighter, something more fundamental was becoming clear. The answer wouldn't come from copying the wing, it would only come from understanding the mind behind it. And line after line, drawing after drawing, a question took shape in their minds. How was this possible? As the engineers measured and photographed every inch of that Spitfire's design, something remarkable took shape in their calculations. The curve they found existed nowhere in German aircraft. Not in the 109, not in the 110, not in anything they'd ever built. What they were looking at was the result of someone daring to break every rule about efficient aircraft manufacturing. The Spitfire's wing wasn't the rectangular, sharp-edged design that German factories turned out by the hundreds. Instead, it was elliptical, a graceful, rounded curve flowing smoothly from the center of the fuselage to each wingtip. It looked elegant. But that was intentional form and function were one. Here's why that ellipse was revolutionary. An elliptical wing distributes lift evenly across its entire span. No wasted energy at the wingtips. With a rectangular wing, lift clusters in the middle and drops off sharply at the tips. This creates induced drag turbulent air, spiraling off the wingtips that eats up power and kills your turning ability. But an ellipse spreads the lift perfectly. Air flows smoothly over the entire surface. No wasted turbulence, more efficient lift, tighter turns. In combat, that was everything. The British designers understood something fundamental. Eliminate the wingtip inefficiency, and you beat every fighter in the sky in a turning fight. And they proved it. Throughout the Battle of Britain, Spitfire pilots outturned German 109s again and again. The 109 was faster in a straight line, that was proven. But in a turning dogfight, the Spitfire owned the sky. Pilots reported the Spitfire could sustain turns. The 109 couldn't match without breaking away. And in air combat, where half seconds decided who lived, that was the difference between coming home and not coming home at all. But the ellipse had one more advantage. Its shape meant the wing stalled gradually, predictably, not all at once. When a wing stalls in combat, you lose lift and die. But the Spitfire gave pilots warning. A gentle stall they could feel coming, time to recover. The 109 stalled sharp and deadly, with almost no warning. Not a mistake in design, a calculated choice. The Germans opted for an abrupt stall in exchange for easier manufacturing. They prioritized production speed over handling finesse, and here's where the bitter truth set in. The German engineers understood exactly how to build this aerodynamic advantage. They had the math. They had the wind tunnel data. They could explain with complete certainty why the ellipse outperformed rectangles. But understanding something and building something are not the same thing. Building an elliptical wing at scale required a completely different manufacturing approach. The Spitfire's wing spars, the load-bearing beams followed curved paths, not straight pieces bolted together. Each spar was unique, curved, requiring precision jigs and handcrafted fitting. Supermarine had created a whole system of molds and jigs specifically for curved components. It was slow. It was expensive. But it worked perfectly. German manufacturing philosophy was built on opposite principles. The 109 was engineered from the start for mass production. Straight spars, angular ribs components you could cut quickly and assemble in sequence on an assembly line. Thousands of workers could perform simple, repetitive operations. That's how Germany churned out fighters by the thousands. That's how they kept the air war going. But this system couldn't adapt to curves. You couldn't mass-produce curved spars without rebuilding your entire factory system. Willy Messerschmitt made that choice years before, when the Spitfire was still on the drawing board. He chose quantity over perfection. He chose a philosophy. 10 fighters that could be built quickly mattered more than 5 that handled perfectly. This choice was embedded throughout German aircraft production. In the factory tooling, the supply chains, the whole system. Changing it mid-war while trying to meet production quotas? Impossible. So the German engineers stood over that disassembled Spitfire, facing a humbling reality. They understood exactly why the British had the advantage. The math was clear. They could sketch that wing, explain every principle that made it superior. They could even design an elliptical wing fighter on paper. But they couldn't build it. Not without dismantling their entire production system. Not without cutting fighter production precisely when they needed every aircraft. This wasn't about talent or technical skill. German engineering was world-class. The problem was inflexibility. Germany had optimized for quantity, and that very choice prevented them from adapting when they encountered quality advantages. The Spitfire's wing became a symbol of their trap. They decoded the secret, but knowing the answer didn't solve the problem. This realization forced a complete shift in German air strategy. They couldn't match the Spitfire's handling. They couldn't copy the design, but they could pivot their tactics. Understanding the enemy's advantage meant rethinking how to fight the air war entirely. The German High Command faced a harsh truth. You can understand an advantage and still be unable to overcome it. The engineers had measured every curve, calculated every coefficient, proven why the elliptical wing was superior. The mystery was solved, but the problem remained. They couldn't out-engineer the British, so they'd have to outthink them. What followed was not defeat but adaptation. German tacticians shifted strategy with brilliant pragmatism. If Spitfires dominated in turning fights, then 109 pilots simply wouldn't accept those terms. The doctrine changed. Boom and zoom. Attack from above with speed and altitude, strike hard and break away before the Spitfire could use its turn advantage. We can't outturn them, the strategy accepted bluntly, so we won't try. German pilots reorganized their formations for a completely different fight. Not synchronized dogfighting pairs, instead, tactical coordination. One element climbs for altitude while another provides cover. The 109's thin wing. Once a weakness in sustained turning became a strength. Faster acceleration, quicker climb, the ability to brake and run. They couldn't copy the Spitfire, but they could weaponize their own design's advantages. Forced to accept limitation, they invented superiority in a different dimension. The inability to match became the spark for tactical brilliance. But behind all this, the engineering, the tactics, the struggle, was one man whose story transcends military history. Reginald Joseph Mitchell died in 1937. Cancer, age 52. 7 years before the Spitfire would save British skies. He died knowing his design was revolutionary, but he never saw that revolution vindicated. He never witnessed his creation saving thousands of lives. That absence makes this human story more tragic. Mitchell designed something impossible without knowing if it would matter. He rejected conventional wisdom because he believed better existed, not because the future promised him vindication. The elliptical wing wasn't born from ambition for glory. It came from an engineer's conviction, almost desperate, that British fighters needed to be better. He was right. He died before seeing it. The Supermarine team didn't abandon what Mitchell created. Faced with production challenges that would have broken weaker commitments, they held the line. Every Spitfire variant from Mark I to Mark II kept the elliptical wing. Not by accident, because they understood what made the aircraft special. They refused simplicity when excellence mattered more. The pilots who flew the Spitfire trusted something they couldn't explain. They trusted the design. They trusted the curves because they felt them in the response, in the tight turning radius, in maneuvers that shouldn't have been possible. Many of these pilots came home alive because Mitchell's wing gave them an edge measured in fractions of seconds, an edge they couldn't measure but could always feel. And across the channel, German engineers, the ones who understood better than anyone what they were facing, gave Mitchell something he never got in life: recognition. They knew the design was brilliant. They understood the engineering courage it demanded. They proved what other nations would later confirm: this wasn't just a good fighter. It transcended what conventional thinking said was possible. That crashed Spitfire carried a lesson beyond military tactics. It proved that manufacturing excellence rivals design genius. Britain's choice to prioritize quality and precision, to handcraft those elliptical curves, despite the cost and complexity, was itself a victory. Germany excelled at volume, but Britain mastered precision. And precision, when it matters, beats volume. After the war, aviation designers would trace modern aerodynamics back to what Supermarine did with that elliptical wing. The F-86 Sabre used principles directly inspired by Mitchell's geometry. Today's aircraft still carry forward aerodynamic insights that began with one engineer refusing to accept what conventional wisdom said was impossible. This story carries a lesson that goes beyond aircraft. Innovation demands the courage to reject conventional wisdom, not recklessly, but from genuine belief that something better exists. It requires manufacturing discipline, choosing quality when simplicity would be easier, It needs designers willing to work without recognition, engineers who persist despite complexity, pilots brave enough to trust designs they didn't create. The German engineers learned something crucial from that wreckage. The greatest competitive advantage isn't what your rival can copy. It's what they can't. It's the courage to design differently, the discipline to manufacture precisely, the commitment to excellence through generations long before the world understands why it matters. Mitchell's elliptical wing endures, but not for solving an aerodynamics problem. It endures because it answers a deeper question. Can one person's vision, pursued with courage and integrity, echo beyond their life and change history? That Spitfire lying in a French field in 1941 was more than twisted metal. It was a message sent by a dead designer to engineers he'd never know. And the message was clear. The best advantage is the one your enemy cannot copy. If this speaks to you, the engineering brilliance, the unconventional courage, the precision that defied convention, then you understand why the Spitfire matters. It's not just about a fighter. It's about what's possible when you refuse to accept limits. Buried in military archives are more stories like this. Moments when human creativity broke through impossible. Engineers who saw differently. Designers who built what experts said wouldn't work. The people behind the innovations. Subscribe to find them, because the greatest legacies don't always come from the names we know. They come from the visionaries who had the courage to build what the world said couldn't be done,